And so we have, as I mentioned before, you can see here the set of integers. It's my representation of the set of integers. And in this case, they're actually generated by 1. So basically the idea of group generation, or finitely generated groups, is something like the idea that every element in this group can be generated by, meaning can be written as some function of, or some expression of these generators, right? We have a set of generators. In this case, it's 1. It's actually, we start with a pretty basic example of the integers. And with the ideas, I say, with the ideas of addition and subtraction, which are really our operations. Although, one interesting point I'd like to make is that subtraction, right here, I'm going to actually highlight that, if I can. So subtraction can actually be considered to be a form of addition. So it's a specific case of addition, because we basically, subtraction is just saying adding a negative kind of number. So what that actually means is that we're adding, and since 1 is our generator of the group, we're basically adding the inverse of 1, right? And that happens to be -1. We see that here, but and again, this is a very basic example. I'm not trying to be mean. This is surely this is obvious to you, but subtraction is really just adding the inverse of some element, and that's allowed using group generation, right? So it's, in that sense, it's generated by 1. That's, yeah. So therefore, the set of integers is a finitely generated group. That's what we can say. We also happen to know that it's abelian, as I mentioned before. It's commutative. It's pretty obvious from inspection. But I'd also like to describe, just briefly, what a subgroup is. So a subgroup, it's actually pretty obvious based on the name. It's a smaller kind of group, which still obeys a group law within itself. But I wanted to make that clear. So, 3, for instance, can simply be expressed as 1 plus 1 plus 1. Clearly, they sum to 3, so if we evaluate that, we get 3. And 3 obviously is an element of this group, so we just add 1 to itself that many times, and that's the way it is. So it's expressible as some function of this generator, I think. But we have quotient groups, and that's what I'm going to get to next. But I want to make sure you understand subgroups and group generation. So quotient groups we have is, now this might look a bit confusing at first, but we have a quotient group if we see one numerator group, so to speak, being modded by a second smaller group, which we define to be equal to 0. And quotient groups, evidently, are the dual of subgroups. In category theory, we have the idea of dualities between ideas, and that has meaning in more complicated ways, which I'll get to later. But just, if you'd like to remember that, you can. It's just a bit of extraneous information for now. Now, furthermore, we have something called a commutator element, or commutator value. It's a very interesting computation, actually, that we can do on any two elements of the same group. So basically, if we have, it's denoted, this is from Wikipedia, it's apparently denoted with a bracket g comma h. And we have this value, it's g inverse times h inverse times g times h, basically. And it's usually defined in this way. We get a value, and if this value is equal to the identity element for all elements, then we know that it must be abelian. And I know this is written in perhaps a bit of a confusing way. We have G inverse times H inverse, even though the group operation might not necessarily be multiplication. But basically, if we choose any arbitrary elements, two arbitrary elements, and we get the identity element for each commutator, then we know it must be abelian. And that might not be obvious at first, but I do have an explanation for that. Let's say we have positive 2 and negative 7. Let's say G is positive 2, H is negative 7. Well, you know, G inverse, actually, we should be evaluating this from right to left in many cases. And with this kind of phrase, I'm pretty sure. With this kind of expression, pretty sure we go from right to left. That might be failed. But either way, 2 plus negative 7, which is negative 5, whatever it is. And then we have H inverse, which is positive 7. So 7 plus 5. Excuse me, 7 plus negative 5. That was also derp. And G inverse we know is negative 2. So 2 plus negative 2 is also 0. And 0 is our identity. Maybe you didn't follow all of that. But the idea is that you can tell. In fact, I think this is a biconditional kind of statement. Because if it's abelian, then it also goes the other way. And we can see that kind of multiplying these together, you know, we know that G to the G inverse times G would give us 1, assuming, or the identity element, more generally. And H inverse times H would also give us our identity element. And the identity element operated with itself would obviously just give us the identity again. So it works that way. If we multiply all these together, find the product of all of these, G inverse G, H inverse H, assuming it is commutative, then clearly we're going to end up with 1. Or 0, depending on our operation, obviously. This is speaking very abstractly, but I'm sure you got the idea. And of course, the set of commutators isn't necessarily a group by itself. However, we can generate one from this set, and that can give us some very interesting information. It's called actually a derived group. That's typically what it's called. And I'd like to show you. Here's some interesting information about functions, actually. So we have an injection, which is a kind of function, whether it be a homomorphism or a functor. It doesn't really matter, because this is very interesting stuff. Functions. This is just general information about functions. I'm sure you probably recall these phrases being mentioned before: monomorphism and epimorphism. And so basically, this is the way they're defined in some sense. I know this, again, this is all very abstract. We'll see some examples soon. But we're just making sure, in any kind of injection, that every output value, so every value that can be outputted by any kind of function, and that basically is represented by a codomain, is met, or is attained by, at most, one element of the domain. And a good example of this would actually be... What would be a good example of this? At most, one domain. Consider any linear function you know. I'm sure you were taught in secondary school about some kind of function, some kind of linear function. Usually they describe these in algebra, like elementary algebra courses, any kind of linear function, assuming it doesn't have an undefined slope. Assuming the slope is defined, we're not dividing by 0 yet, at least not in this context. So y equals kx, or y equals mx plus b, something of that form where m is defined. Then we know, really, that every output value, every element of the range, which, by the way, must equal, or the range must include negative infinity to positive infinity. So, basically, all real numbers, if you choose to use real numbers. Technically, there is some debate about the real numbers. Or at least there has actually, historically, been debate about real numbers and the continuum. It's actually a very interesting historical problem, which I encourage you to look up. But that's not quite our topic right now. We're considering whatever set you want to use. Whatever non-zero set, like the integers or the rationals, or perhaps the real numbers. Assuming that's our codomain, so we're considering all real numbers as our range, or all rational numbers, we know that every output value must be attained by at most one domain. You know, that condition is met, therefore the function, that linear function, whatever you're picturing, whether it be y equals 2x, or something like that, then we know every output value, say, I don't know, y equals 4, must be met by at most one domain. Well, you know, in the example I gave, let's just think about that. Y equals 2x, assume it passes through the origins, so c is equal to 0, or b is equal to 0, excuse me. Set that equal to our output value, which is now 4. Well, 2x equals 4, alright, x must equal 2. And we know that that's the only solution, actually, considering from an algebraic perspective, by the fundamental theorem of algebra, we know that's really the only complex solution to that equation. So, and that meets the requirement. It's at most one element. I should write that. Element of the domain. That's what I meant to write. And that makes sense. That's in fact satisfied by the function I just gave as an example. I was just making it up on the spot. But we also know that monomorphisms, and we've seen some examples of morphisms. And in fact, my kind of example with the linear function is an example, I think, of a monomorphism. That's if we assume it's a function from a group to a group, so let's choose the group of rationals as our domain, and our codomain is also the group of rationals. Then we know that substituting a rational number in there will just give us another rational number. And y equals 2x, that is. And in many other examples as well, but not all examples, obviously. So that would be a monomorphism. And there's a certain formal mathematical notation, which you can see about that. And you see some other examples here. That's very interesting at all. But we also have something called a faithful functor, right? That's faithful functor is another example of an injection. So we have the same idea, where every individual output value must be attained by at most, and at most is the key word there. At most, it can be 0, or it can be, at most, 1 element of the codomain. And furthermore, we actually have the surjection. Now, it's important not to confuse these things. Surjection is quote-unquote onto, a function that is onto. Now, one-to-one is kind of the informal language for an injection. And you'll hear these when people are talking about mathematics. Let's see here, you hear some professors talking about different kinds of functions, and, oh, is that surjective? I'm not quite sure about that. I'd have to think about it. Or, you know, let's consider, is this function actually injective, you know? Maybe you'll hear that at a party or something like that. Well, now you know. You need to be familiar with those things. I'm really rambling at this point. The idea is, every output value, this is kind of contrasted with an injection. Every output value is met by at least one element of the domain. Again, we have this element. At least one element. That's really sloppy. I'm sorry. I don't have a literal pen. I just have a mouse, so this is not easy to write. But anyways, I think you know what I'm trying to say, though. Every output value is returned or achieved by submitting or substituting, I guess would be a better word, at least one value of the domain. So what's a good example of this? What can I say for this? You know what? Let's just say a linear function whose slope is 0. Whose slope is 0. Let's consider that. So m does equal 0, right? Therefore, the linear function is really just a constant. We can call it a constant. It's just some horizontal line on our graph, if you want to think of it as a graph or a plot, if we're plotting it, you know. But we know that every output value, but in reality, we just have a single value for that, is met by at least one domain. Well, that's absolutely true, because let's think of our domain as being all rational numbers, or all integers, or all real numbers, if you so choose. Well, then, our output value, let's say it's 5, is met by infinity elements of the domain. Well, that's at least one, sure. The one thing I'd like to point out and caution you about this one is that that wouldn't actually work as a morphism, I'm fairly sure, because you see 5, or just one single constant, wouldn't really work as a group, alright? So epimorphism implies that we're going from a group to a group. Well, if we have a constant, that doesn't really constitute a group. There's no identity element, for instance. Unless, of course, we have the trivial group. I believe that's what it's called. It's the group when we have just, literally, just the identity as our element. So the group that is just 1. Or the group that is just 0. Well, we can choose that, I guess. Doesn't always help us that much, but sure, it's the that's what they call it, the trivial group, actually. It's just the 0. You know what? I think I'm going to look that up right now, if you give me a moment. Because I don't know what that's called. So, if I can just exit out of this, I'm actually... This is quite sudden, I realize that. And I'm going to end show. Do I want to keep the ink annotations? Well, do you care? I think I'm not going to keep them. Here is my computer. I'm going to open a new window, and I'm going to say... Can you see that? I think you can. The trivial group. Trivial group. Group consisting of a single element. Yes, indeed. Very good. Okay, I just wanted to fact-check myself on that one. Oh, we have a list of small groups from Wikipedia. Alright. See, I'm being sincere. You can truly get lost in the whole subtopics of group theory on Wikipedia. I'm not even joking. We have categories, finite groups here, and list of small groups. Let's, in fact, click on that. It's really quite fun. They give us so many different examples, so many different explanations. Look at this table. Oh my gosh, it is so good. I encourage you. You can poke around here and really see some very good examples of this. It has been suggested in this article be merged with trivial ring and trivial module to zero-object algebra. Discuss. Oh, well, that's very interesting. Proposed since 2012. What do you know? This is rather interesting. Like, this is recent discussion. Oh, wouldn't that be fun if it were merged? I'm sorry. I'm getting really ahead of myself. Let's go back here to functions, as I was saying. So we have an injection and a surjection. I described those. And you can imagine, if a function is both an injection and a surjection, then we simply get that it's a bijection. And you may have heard this word before, bijection. Some famous people have described it, and by famous people, I'm talking about, like, Day 9 and people like that. Bijection is basically the rigorous mathematical way of saying it is a one-to-one correspondence, literally. It's the best way of saying it. It's saying that for every element in the input, in the domain, we have one element, one and only one element of the range. And the same can be said the other way around. For every element of the range, there's one and only one element of this starting domain, whatever we want to call it, the input. Only one input for every output. And that's pretty obvious to you, I'm sure, because we say at most one and at least one. Well, the only way that can both be true is if it's one. Now anyways, that actually about wraps up the main presentation. So thank you very much for watching. We see some sources here. But before you leave, I'd just like to give a conclusion here. So, my friends, I dream of a world where it is truly common to discuss topics in science and mathematics in everyday discourse. A world where history, biology, chemistry, physics, and especially pure mathematics are as frequent topics of conversation as sports and the weather currently are. A world where there is genuine, near-universal interest in these topics, rather than a widespread fear, blithe contempt, or outright disliking of anything that is remotely academic. This is not a mere complaint that the whole world should simply change just because I say so. Rather, this is an honest argument in favor of the advancement of all our intellectual needs. In short, we need a second enlightenment in our society and culture, from which we will all benefit.